I will work out through two simple linear examples of maps which have very simple itineraries that you will understand, so temporal dynamics, and a very simple and beautiful relation between temporary and spatial dynamics. And as you'll see, understanding how things are ordered spatially is totally essential to our progress. Bernoulli shift map, also known as coin toss, 50-50 probability to get one or other outcome, is a deterministic system that mimics probabilistic process of throwing a coin. It's a map defined on unit interval. We'll call this axis G, gamma between 0 and 1 at time n. And at time n plus 1, the outcome is on the left-hand side, you get stretched over the whole interval. And we'll call this branch of a function B for Bernoulli, 0 for left part of the interval. But if you're in the right half of the interval, you also get stretched over the whole interval. We'll call this B1. So the formula is very simple. B is a function of gamma consists of two branches. Left branch, in there you take gamma and multiply it by number 2, and right branch where you take gamma, multiply it by 2, but then you subtract 1. So you're still on the unit interval. You apply the left branch if gamma is in the left interval, which we'll call partition 0, which is start any place for 1/2, and we'll make it open. We'll exclude this point where map is not defined. Or it's in an interval called 1, which starts a little bit to the right of the so-called critical point and goes all the way to 1. But we'll call that point, we'll call it the critical point. So it doesn't happen. And dynamics is very simple, and it's really just a shift map in the same sense that we define shift when defining symbolic dynamics. If you, for example, have starting point gamma to be 0, 1. So it's any number in a unit interval, and it's convenient to write in a binary basis because you'll be multiplying by number 2. So binary is natural. And in binary number is an infinite sequence of binary digits. And now when we apply the Bernoulli map to it, what does the Bernoulli map do? It multiplies every element, every binary number in the sequence by 2, which means it just shifts it by 1. So for example, this would be binary 1/2. If we multiply it by 2, we get 1. But 1 is off the end of our interval. That's why we have this -1 here. So we find out that we get a map number 0. So this shifts to the left, 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 and so on. So nothing can be simpler. That's the action of the map on number in binary representation. Now, critical map, which seems to be trouble, is actually godsend. If you look into the past, I suppose before I do this, I can immediately classify some invariant solutions of this. For example, this point here is a fixed point of the map. So clearly, one of the fixed points is 0, which is just one point, and that point is gamma 0, which is just 0.0000 forever. And there should be also a fixed point 1, which you can ponder, but we have allowed ourselves to include the right interval there. There is clearly a cycle of length 2. Let's call this point gamma 0, 1, and let's call this point gamma 1, 0. So this is P equals 0, 1. That consists of 2 points, gamma 0, 1 is a point that starts on the left, which is our partition 0. Then it lands on the right, which is our partition 1. So first digit is 0. Then it ends on the right. Then it ends on the left. Then it ends on the right, and so on. And this goes on forever. So this is 0, 1, repeated infinitely many. And then that's this periodic point. That's its symbolic sequence or itinerary. And then under one iteration, it ends on the right side. So there's a second periodic point, which is 1, 0, repeated forever. See, here we have a wonderful situation where the symbolic dynamics and binary coincide.
Oh, really? Okay.
So that's why I use the symbol 0, 1. I could have called them left and right, etc. But in this particular map, the symbolic dynamics is binary. Is the binary number. So we say, in some situations it's really easy to compute these points. That means that, it'll be no problem for you to figure out what this sum is, and you'll know exactly where all the periodic points of this problem are. You realize everything is allowed. So this will have any possible sequence of zeros and ones will be realized by this map as an invariant solution, time invariant solution. If it's a finite block repeated, you can specify it finitely. If you write an infinite sequence, there'll be a unique point, and it's under applications of the map, that point will move around, but that will be the unique solution for any sequence. So this map, a binary number, which is actually just a number on a unit axis in a natural basis, happens to coincide with symbolic dynamics. So temporal itineraries tell us stuff. Any repeating block will give me a periodic orbit. And all repeating blocks are allowed because all sequences are allowed. So if you just say, I would like to look at the binary number down here, which is specified by saying 0, 0, 1, 0, 1, 1, repeated forever. I say, oh, that's a 5 cycle. And
how do you know it's a 5 cycle?
Because it's repeating block of length 5. Which means after 5 iterations, you do the same thing over and over again.
Oh, right, because you're just shifting. Right.
And because it's infinite, see, if I specify, as you'll see in a second, if I specify any finite number of things, you don't know it's a periodic orbit. You just know that it starts with finite sequence. If it does it twice, you start developing suspicious it's a periodic orbit, but it's still just an interval. It'll be an interval in binary numbers. If it's the cycle is length 5, and I specify repeating sequence twice to be length 10, so it'll be something that's very narrow. It's 1 over 2 to the 10. But it's still an interval. Everybody in that interval shares the same history. I'll just show what these intervals are. But if you have the infinite sequence, the interval has shrunk to 0. So I know that I have all periodic orbits in this case. And I know how to compute them all analytically. And in this case, stability will be trivial because it's 2 at every time. So I'll know the stability of all periodic orbits. So I'll be able to do lots of hand exercises using models like that. Another aspect of this model is that critical point, which seems like a pain, but this critical point has the following property, that it's pre-images. I take the map, and I take its inverse, and then I do a little counting, and I write it the way that. Now, what are the pre-images? If I look at this thing, pre-image is something that maps into it. So there are 2 points which, under one iteration, map into critical point. And they're well defined. Even though the value of this thing is not defined, the pre-images are well defined. So there is a B0, the left branch of critical point here, and there is a B0 minus 1. So this map is deterministic forward and future, but backward and future it has pairs of solutions always. So I pick both of them. I have to specify which one, and that I do by saying which branch I pick there. P1, oh, gamma C. And what's happened now? Now I have 4 neighborhoods. In this neighborhood, which I'll call M00, everybody stays on a left branch in 2 iterations and then does something. So they share the common future. Again, always excluding the partitioning point. In this neighborhood, I start on branch 1, but I end up on the other branch. So it's M1. In this neighborhood, if I go 1 and 0, everybody follows 1 and then goes to 0. And in this neighborhood, which is close to this fixed point, which will be repeat of 1 infinitely many times, I have 1, 1. Everybody who starts this shares common future of being on the right side for 2 steps, and then something will happen. So now what I see is that the pre-images of critical point, they act like a knife. You know, critical point is a sharp thing that actually divides. When you think about this map, it's a map in which what you do is you take an interval, you stretch it by a factor of 2. That's this number 2, this one. And then you say, okay, let me cut this thing in half, and I overlay leaf upon leaf. And that's what this map is. So you stretch and overlay, stretch and overlay. So if you had some kind of slicing machine, that's how you produce more and more layers in this kind of map. So it acts like an edge. It's not continuous at all. And it's a pain, but actually it's powerful because that point itself defines all partitions of this dynamical system. So having critical points is really wonderful, turns out. And Lorentz system that you should have looked at if you did the exercise. Lorentz system is a nice example that has a return map, Poincaré return map, which has a cusp. It has a singularity. That singularity is caused by the fact that unstable manifold has to somehow cross the invariant subspace, which is the z-axis, and it can't do it. And that produces, that point itself kind of slices up into, crisps us into 2 things. So these singularities, which might seem not nice because we're interested in smooth dynamics, if you have them, can help you a great deal if that happens for you. And this is the simplest example. So now we have everything. And one particular thing now we can see we always obtain in a system like this, we get a partition in 2n regions, where each region can be specified by the future of the points in it, the common future of the points. So let's call them symbols J1, J2 to Jn. And that's just the set of all initial points gamma which share first J binary digits, Jn, and then anything can happen, where J is either 0 or 1. The time itinerary is very simple. It's any sequence up to infinity, and any such is allowed. So you just tell me what you want, and I tell you that's your orbit in physical space. Remarkable thing which you don't appreciate yet is that we actually also have a spatial ordering. So if you take 2 points on the original map, if gamma of A is smaller than gamma of B, then A is to the left. So, you say, well, that's obvious. But what it says is that, so you give me an itinerary, I compute gamma from that itinerary. It turns out to be, I just compose it together as a binary number. You give me another itinerary, and I say, aha, this point is over there, or it's over there. So I can start ordering points in space just by knowing their time dynamics. It's so simple that you pay no attention to it.